My today's topic is based upon generalization of mean value theorem. I'm going to discuss the Taylor form, or sometimes it is called Taylor's theorem or Taylor series, whatever you can call it. So let's first of all let us write the theorem, the statement of the theorem, and then I'm going to show you some of its special cases and their applications as well. Okay, so Taylor's theorem goes like this. Taylor's theorem, and it is very important. The proof of the Taylor's theorem is not there in the syllabus, so you don't have to be bothered about proofs. We shall only try to memorize the statement of the theorem, and we will learn how to apply it on different problems and interesting problems. Let small n belonging to capital N means the set of natural numbers or positive integers. Let I is an interval AB, and let us consider a function f from the interval I to R be such that f and its derivatives first derivative, second derivative, nth derivative are continuous on the interval I, and n plus 1th derivative of f exists on the interval open interval AB. If x naught be any point of the interval I, then for any arbitrary x belongs to I, there exists a point C between x naught and x such that we have the following expression. Now you have to memorize the expression which I am going to write right now. The expression goes like this, that fx is equal to f of x naught plus f dash x naught plus f dash x naught into x minus x naught plus f double dash x naught into x minus x naught whole square by 2 factorial, okay, plus f triple dash x naught into x minus x naught whole cube by 3 factorial. In this manner, if I go, then the last but one term will be fn x naught by n factorial into x minus x naught whole thing to the power n, and the last term will be f of n plus 1, sorry, fn plus 1, n plus 1th derivative of x of the function fx at the point C divided by n plus 1 factorial x minus x naught n plus 1, and the series which I have got in this manner is called the Taylor series. The series which I have got in this manner is called the Taylor series. So I have taken this expression, I have considered this expression from the book of the note which I have shared with you. So you can get it from there also. And this part which I have written over here, I am marking it with green color. This part is very important, and this part has a special name. It is called Lagrange's form of remainder. It is called Lagrange's form of remainder, or sometimes it is called derivative form. Okay, and we shall denote this by Rn. This remainder form is denoted by Rn, and it is n plus 1th derivative of the function x at the point C by n plus 1 factorial into x minus x naught whole thing to the power n plus 1. So that is the thing, that is the entire thing which you have to remember. Now what we are doing, you will gradually know that why this theorem, Taylor's theorem, is so important. Okay, you will come to know of this fact today. And I shall also make you understand what it is actually doing. Okay, why on the left hand side we have fx and on the right hand side we have this big expression, but only we can say right now, because I have to show us a few special cases of this particular theorem, I can only say at this point that this series is a finite series. You can see finite terms, up to finite terms I have written, and not only that, from this particular Taylor's theorem, the original Lagrange's theorem can easily be derived, okay, under some special conditions. Or you can easily see that if I consider this term fx naught plus f dash x naught x minus x naught, only these terms on the right hand side, it's actually the Lagrange's theorem, mean value theorem. So this is all about. So we have the function from which is defined from the interval I to the set of real numbers, and the function is having some derivatives. Nth derivative of the function exists, and they are continuous on I. Every derivative function, every differentiable function is continuous, you know. And n plus 1th derivative of the function also exists on the open interval AB. Then there must exist a point x naught in the interval I, so that for any arbitrary x of the interval I, there exists a point between these two. There exists another point C between x naught and x, such that this holds good. Okay. Now from this Lagrange's form, this Taylor's theorem, we can derive some special cases which is not mentioned in the book. Okay, so I'm going to talk about that. Those special cases are very useful in solving problems, and I shall be solving problems using those special cases. So I hope that you have copied. Let me enable the chat box so that if you can want to write anything, you can. So I can, I'm going to move on to the next page, and I'm going to show you the special cases first of all, and then I'm going to start one problem. Okay. Now, take x minus x naught is equal to h. Okay, so that x naught plus h is equal to x. Then from Taylor's theorem we get now you try to substitute by yourself, you try to substitute h in place of wherever x minus x naught is present in the previous form of the Taylor's series. So in place of fx, you see x is there. So in place of x, we can substitute x naught plus h. So I'm writing over here f of x naught plus h is equal to, in f of x naught will remain same. Okay, f dash x naught, I'm not changing anything, but in place of x minus x naught I can write it as h, and then we can write x naught, x minus x naught whole square as h square by 2 factorial f double dash x naught. Okay, and then we can write h cube by 3 factorial by into f triple dash x naught plus dot 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 plus h to the power n by n factorial f n x naught, and the last one will be h to the power n plus 1 by n plus 1 factorial f of sorry, and n plus 1 is the derivative of f at the point x naught plus theta h. Now look at this term. Look at this term from where this just a minute, you hold on, huh? Just a minute. Just a minute. So look at this term which we have, the last term, h n plus 1, h to the power n plus 1 by n plus 1 factorial, and this thing. And you see here the term theta, the term theta will lie between 0 and 1. The number theta will lie between 0 and 1. And since theta is lying between 0 and 1 and h is positive, h is always positive because h is actually a kind of, it's the difference of x and x minus x and x naught. Okay, so it gives you the distance between the points x and x naught. So we can multiply all the sides of this inequality by h and we get this thing. Okay, and we can add on all the sides the point x naught, so that we get x naught less than x naught plus theta h plus which is less than x naught plus h. And you see this point x naught plus theta h, I am naming this point as c. Okay, and c is lying between x naught and x naught plus h. From here I can write it as x. So probably you are thinking that in the previous case we have written c over here, c as the point, and now in this expression I have written x naught plus theta h. So probably you are thinking from where this x naught plus theta h has come. So I'm actually showing you over here that x naught plus theta h is nothing but the point c. So look at this point, and x naught plus theta h is nothing new to you, because while studying definite integral you have come across this point, I think a minus, or you have come across a point like b equals to a plus nh. Okay, so you have dealt with this type of thing various times earlier. So this is a point like, okay, that a kind of similar structure we have. But the point C, which I mentioned in the Taylor's theorem, that point has a special form, a special expression I can give it to that particular point, and that is x naught plus theta h. So these two things are actually similar. Okay, and it is also satisfying the criteria of the Taylor's theorem, which is saying that C is a point which will lie between x naught and x. So that is one another form of the Taylor's theorem. Now, why am I actually showing you this particular form? Because of the following result, and the following result is very important. So let us now write, take now h is equal to x and x naught is equal to 0, then what will you have? If we take h equal to x and x naught equal to 0 point, then what will you get? We will get fx. Here in place of x naught you put 0, In place of h, you put x. So we get fx. And then on the right hand side, we will get f of 0 plus x into f dash 0. You just check with what I'm writing. X square by 2 factorial f double dash 0 plus x to the power n by n factorial f n 0, and lastly we have x to the power n plus 1 by n plus 1 factorial f n plus 1 theta x. Okay, so we have this this particular series has a special name which I've got from the previous one, and the name of this series probably you have heard is called Mclaurin series. So in your syllabus, Taylor series, Mclaurin series, all are there, but probably you are thinking they are different entities, but not. Mclaurin series is a special case of Taylor's series. Okay, so actually they are interconnected to one another. So this is the thing. Now I'm going to show you a problem. Okay, in the next page. So the first problem goes like this. Example 1. If f of h is equal to f0 plus h f dash 0 plus h square by 2 factorial f double dash theta h 0 less than theta less than 1. Theta is a number between 0 and 1. Theta is any real number between 0 and 1. Okay, theta is any real number between 0 and 1. So sometimes you may come across the Taylor's theorem in the book, in other books, where they have not defined theta, they have not defined Taylor's theorem in this manner. Okay, so I see, as I have written a point C over here, what is the form of C? How does the point C look like? Yeah, of course C lies between x naught and x, but uh, can I express C in terms of x naught and x, or x naught and h? So that expression, that thing has been shown over here. So in some books you may come across this point, that C here, actually C is x naught plus theta h. That is your C. Okay, and theta lies between 0 and 1, a real number lying between 0 and 1. Now FH, the question is given like this, and we are supposed to find theta when h is equal to 1 and the function is given as 1 minus x to the power 5 by 2. That is your function. Function is given, h is given, this expression is given, and from that expression I am going to find theta, where theta is a real number, lies between 0 and 1. So let's first of all, let us solve this particular problem. Gradually, after once the class ends, we are going to understand what is happening. So right now, you try to look at this thing from a technical perspective, how to solve this particular problem. So solution, given fx is equal to 1 minus x to the power 5 by 2. Okay, now you see we actually require these things. F0 is required, f dash 0 is required, f double dash is required. So we are going to calculate f dash x, f double dash x subsequently. So therefore f dash x will be 5 by 2 1 minus x to the power 5 by 2 minus 1 into minus 1. So we get minus 5 by 2 1 minus x to the power 3 by 2. So we have got this. Okay, that is your f dash x, and your f double dash x would be your f double dash x would be minus 5 by 2 into 3 by 2, 1 minus x to the power 3 by 2 minus 1 into minus 1. So we get 15 by 4, 1 minus x to the power half. Now, as a positive, this term will become positive because one negative sign is over there and another negative sign is over there. So that will make the items positive. Now, since we have calculated f dash x and f double dash x, so we are going to calculate these items. Okay, so taking x equal to 0 first in fx, we get f of 0, which is 1. F of 0 is 1. And f dash 0, if I put 0 over here, we get in fx, let us write putting x equal to 0 in fx and f dash x, we get f0 as 1 and f dash 0 will be minus 5 by 2. Okay, and we need to put theta h. Theta is a real number lying between 0 1, so we need to put theta h in the expression in the double derivative of the function fx. Okay, so let us do it. So f double dash, let us now put theta h, x equal to theta h in f double dash x, and we get f double dash theta h, that would be 15 by 4, 1 minus theta h to the power half. Okay, so everything has been obtained. We shall now put all these items. Let us name these items as 1. So we will put the items given in 1 in a given equation. So we can name the equation as star. This is your star. So we'll write putting everything, putting all the values from 1 in star, we get the following. So one more thing, here on the left hand side of star we need f of h. So it would be nice if I write f of h if I include f of h in equation 1. Okay, so we can write here that f of h will be 1 minus h to the power 5 by 2. Also, you can write here also. Okay, so this is also a part of equation 1. So we are going to put all these values in the expression. So we get, therefore we get f of h is 1 minus h to the power 5 by 2 is equal to f0 is 1 minus 5 by 2 into h plus h square by 2 factorial and multiplied by 15 by 4, 1 minus theta h to the power half. Okay, so we have got this. Now they have asked us to put h equal to 1 in the expression. So we are going to put h equal to 1 in the expression. Putting h is equal to 1 as given in the question, in, let us name this as equation 2. In 2 we get, okay, let us put h equal to 1. So if I put h equal to 1 here, we will get left hand side will become 0, and on the right hand side we will get 1 minus 5 by 2 plus h square by 2 factorial. So 1 by 2, that is from here, and 15 by 4 from there. So that will be 15 by 8, and 1 minus theta to the power half, because h has become 1. So I hope you have written up to this particular point. So if you have done so, I'm moving on to the next page. Okay, so if you have not finished, then you can tell me you can write in the chat box. Otherwise, you don't have to write anything. I'm moving on to the next page, and the rest part of the problem you can do very well, because we are going to solve this particular problem for theta, particular equation for theta. So the expression which I have got, 0, 1 minus 5 by 2 plus 15 by 8, 1 minus theta. So from there we can write it as 5 by 2 minus 1 is equal to 15 by 8, 1 minus theta to the power half. And this is equal to 3 by 2, 15 by 8, 1 minus theta to the power half. And this is, we can write it as 1 is equal to 5 by 4, 1 minus theta to the power half, or we can write it as 4 by 5, 1 minus theta to the power half, and we can square both the terms, both the sides. So that will become 1 minus theta on the left hand side. I mean, I'm just reversing the equality. So I'm writing the right hand side first and then left hand side. So you just rotate it. Okay. So we get 16 by 25, and from there we can calculate theta to be 1 minus 16 by 25, and which is 9 by 25. And 9 by 25 is a number obviously which is lying between 0 and 1. Okay, so this solves the problem. So what is happening over here? From this particular problem, I must say that you have understood that we have calculated something. But we have not understood what is happening inside. Okay, since the session is ending, I know very much that the next problem when I'll be doing very next problem which I'll be doing in the class, that problem will actually give you the feel of what Taylor's theorem is doing. Not this one, but if I start solving that problem, the problem is a bit long, so it takes time. So therefore, I shall not be able to finish it in this particular session. So let's discuss about something. Let's discuss about what Taylor's theorem is actually saying. Okay. You see, Taylor's theorem is actually a kind of approximation. You are approximating a function fx with the help of some other things, some other terms, like the function the value of the function has been found at some point x naught, and we have calculated some terms like x minus x naught and their difference, and x minus x naught by whole square by 2 factorial. All these items have been calculated. And with the help of, and derivatives have also been calculated at that point of the function. With the help of this function, we are trying to approximate the given function fx. Now here in this particular problem, and similar case with is with this and that. Okay, same thing. Now here the function was actually given as 1 minus x to the power 5 by 2, and this expression has been written using the Taylor's theorem, and from there they are trying to identify the point for if h, the width, the gap h means what? When you write x equal to x naught plus h, if you take h equals to 1, that means what? So you are adding 1 to each element. So x naught plus 1 gives you x like this. It goes on like that. So with this one, okay, a plus b equals to a plus nh. If you take h equal to 1, n equal to 1, what will happen? So similar thing is happening. It's the gap is 1, unit gap. So if I take this, and what will be the point theta? What will they are trying to identify the point C that has been mentioned in the Taylor's theorem, and by that they are trying to approximate the function's value at the point h. Okay, so and from there they are trying to identify the point C in terms of theta, where theta lies between 0 and 1. I know that this problem is not a, it's just a technical problem. The feeling of applying Taylor's theorem is not actually coming to our mind. Now the feel will come in the next problem. Before I start saying anything about my next problem, which I'll be doing in the next session, I must ask you one thing. Suppose I'm giving a number 2, and I am asking you to approximate the square root of 2. If I ask you what will be the approximation of this number, we know root 2 is an irrational number, and from our childhood days we have come across that root 2 is equal to uh, approximately is equal to 1.414 and so on. Okay, so it is an irrational one. Irrational numbers are those numbers which are non-recurring, non-terminating decimals. But we have calculators. We can easily find root 2 up to certain decimal points. We can using computer we can calculate root 2 uh, more accurately. With supercomputers we can calculate root 2 up to several decimal points. But imagine, suppose we do not have these tools, then how can we approximate this particular function root 2? How can we approximate root 2 without taking the help from without taking the help of technology? Can I guess that root 2, a new number has been given to you? Can I guess what could be the value of root 2? Even if I cannot guess it, can I say that between these two numbers root 2 may lie? Okay, or suppose you are familiar with root 2, then suppose I am giving you a number like 1.75 and the square root of that. Okay, this number, immediately you cannot say what is the square root of this number. Okay, so can I guess this number will be having some values lying between this and that point. Okay, so in the next problem I'm going to show you that this can be done using Taylor's theorem. Taylor's theorem was developed in those days when no technologies were available. People did mathematics to approximate functions, and these various theorems were actually devised. Even if today, even the technology is available, Taylor's theorem is very much helpful, because you see that when we talk about computers are classical computers, and you even if you write some kind of programming, computer will give you the value of root 2 up to certain decimal points, but it cannot give you the actual form of root 2, because root 2 is irrational, and the number of spaces, decimal places, a number of places after decimal points, they are actually infinite, but your computer has a finite space. So therefore uh, calculating root 2 using calculator or computer is okay, it's helping us, but this approximation is somewhat incorrect, because it's not giving me the actual value. In the function also, you are not trying to find the value of root 2. In this type of problem you'll be seeing that I'm not trying to find root 2, but at least I can get, yeah, root 2 is the kind of number which will lie between this and that. Okay, so therefore that thing I'm going to show to you in my next session. So let's wait for the next session to begin. Meanwhile, you write your roll numbers in the chat box, because the time is running out and I have to save it. So quickly you do.